right? So now we were looking at one concrete example just to, before we get to generalization of all this and then prove theorems. So as I told you, right, our experts will be constraints, right? Now the intuition is that they are going to penalize in a way that uh, people whose constraints are not satisfied, I mean, they get less penalized comparatively. So what could be the corresponding weight function? What could be the corresponding weight function? What could be the corresponding cost functions, right? Do you get my questions, right? Okay. So if we are going to have an updation of solution, think of this, okay? Think of this step, right? So what will we do? So now for this, these rounds will be like, in each round will produce a solution, okay? Think of this way, that in each round we'll produce a solution, like we produce a feasible solution, or we'll try to produce a feasible solution, okay? But it may not be very good, like I will try to produce a solution that may not be satisfying all the constraints, okay? We will get to that, right? But that is the whole idea. The whole idea is that this is going to produce some solution, like maybe not feasible in the beginning, but at the end, whatever it will produce after a certain number of rounds, it will be a feasible solution, and we will also be able to show that it's a feasible solution of low cost. Okay, so that's an idea. So each round we will be producing a feasible solution. Okay, now we say choose an expert I, follow his advice with probability proportional to its weight, right? So this weight will now correspond to what you have produced in the tth round, right? What is in the beginning? What is your solution, right? And after ith stress, we would have done something to the weight, right? And that will be corresponding to the sum x, that is like your solution in some sense. But this we will do slightly differently, okay? You will see in a minute. And okay, and so these weights will just remain this, but will change the penalty. Like, so we will have this weight function. Now based on this weight function, we will ask for a solution. Given these weight functions, I'll ask for some solution. But that weight, how do you give this weight functions, right? This cost business, right? That will decide how things are, okay? It's a bit vague, but let's try to formalize these things in a bit more appropriate way. What do I mean by this? Look, so for now, what is a covering LPs? How does a covering LP look like? The covering LPs, or say, for now, let's say, basic feasible problem, okay? And we can make this basic feasible problem. So here is a convex program. Okay, what is a convex program? Does there exist x question mark x in P, this is convex. You know what this convex means, okay? Convex means if you take any 2 points and draw a line, all those points lies inside this region. So this is convex. And what is the constraint? Ax is greater than equal to b. Ax is greater than equal to b, okay? Where A is in R m cross n, right, matrix, X is in Rn, okay, and P is a convex set. Okay. So this is my goal. Okay. So somehow we will think of this like these represents easy constraints. Somehow it is easy to satisfy them, okay? And this A gives us some hard constraint, because these are also constraints, so we should have also an expert for all those, but they are like an easy constraint, so we will not worry about them, okay? So, but these are my hard constraint, okay? So the idea is for this kind of algorithm is that, look, maybe satisfying this is hard, but imagine yourself that if I gave you just one constraint, it might be much easier to satisfy it. If I did not give you multitude of constraints, but just one constraint, then maybe it is easier to solve that in practice, okay? That is easier to solve, right? So in particular, let's ask ourselves following linear combination. Let P1, P2, Pn be greater than equal to 0 such that summation Pi equal to 1. So this is like a probability distribution, okay? And I would like to, okay, this is what it is. So look, what I would like to solve, or let's see how to say this, this is becoming a bit tricky. Okay. So we will assume the following oracle. Suppose we have an oracle for following which tells us what? Which are given a probability vector on m constraints, it says P transpose this is a vector, Ax is greater than equal to P transpose B. So what is this? If you write down, this is basically a linear combination of all the constraints. So if I no? Okay. Okay, so I could have also written, let's write it down. Look, what is P transpose? If P is a column vector, right? Think of this way, P1, P2, dot, 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 Pn, this is your A matrix, right? This is like A11, A12, A1, what was that? M cross n, so A11, AM1, AMN, right? And here it is x1 up to xn, right? So if I take this, what is this? P1, this, P2, this, right? P3, this. So if AI is like a row vector, then P1 multiplies to which all things, if you notice? P1 multiplies to this, right? What is this? If you multiply this, what you will get? P1 into this, P2 into this, P3 into this, Pn into this, P1 into this, P1 into, right? So if I can, so this is nothing but Pi AI, right? I going from 1 to n times x. or I can also think of this as a vector, right, dot x, right. So I first multiply these two, then I will get this dot vector, right, and it's dot producted with x, right. So this is exactly what this constraint is, and I have multiplied P transpose B, which is nothing but summation no, it should be M, no, yeah, P1 to Pm, because we have experts, otherwise this is, what is, I didn't get it, okay. So I equal to 1 to M Bi, agreed, this is all that it is, okay. So suppose this oracle told us two things. Why? Because look, now all I am asking is this one particular equation satisfied or not, okay. So this is an oracle we will assume, suppose this, what is the point of this oracle? It will say, look, I cannot satisfy this, then can I say that my original program is not feasible? Because if x was feasible for this constraint, the same x is also feasible here. So if it says no, I definitely have no, because yeah, I have just multiplied with some non-zero quantity both sides, so what's the big deal, right. So if it says, this oracle says no, means what? If it says no, means initial convex program, initial program is no. But if it says yes, we will do something about it, right. So if it says yes, it has given me some xi values, right, I will see what happens here. It might be satisfying everything or it might not be satisfying everything. If it satisfies everything, then we are happy, we are done, right, okay. But notice one thing, that in general this is like a feasibility problem, but if you would like to solve an optimization problem, then we have to convert an optimization problem like min, max, right. Generally what is, right, what we like to do? We would like to do min summation some some Ci xi, right. We also have such kind of constraints, right, such kind of constraints, and then we are looking for a point which maximizes this, right. I am not only looking for a feasible set of constraints, but I am also looking to minimize or maximize something, but that is very easy to convert into a feasibility problem. You can just do a binary search on the solution in many cases, right. So for example, I could have guessed a value L, right, of this value, and I would have said what? Then I would have put this summation Ci xi is less than equal to L, right. And in most cases, look, if I do binary search, it's like it is only going to add n iterations in wise, because look, value of xi, whatever it is, like if we know that it is some bounded program or something, right, you have to only return in polynomial many bits. So the value, it can be only 2 power poly in that. So 2 power poly into some n or something is only going to become another 2 power poly. So if I do some sort of binary search, at least for most decent program, a binary search will be helpful for us. Do you get my point, right? So I could do something of this nature. So for now, let's try to just concentrate on this decision version of the problem, okay. So this is an oracle which we will like to have with us, okay. But right, so look, what happens is that, I mean, such kind of optimization problem to exist because we only need to check the feasibility of one constraint rather than some m constraints, right. So hopefully it turns out to be much easier than the other, okay. right? And we already said if it satisfies yes, then this is yes. But if it is no, then it is definitely no, right? But if it is yes, that doesn't mean that this is yes. Because all you have solved is like, I have satisfied my constraints on an average. This is like satisfying your constraints on an average. Constraints on an average. Right? So if you satisfy constraints individually, you will also satisfy constraints on an average. But if you satisfy some constraints on an average, that doesn't mean that you will satisfy every constraints individually. This is a point to collect. Okay? At least this is my understanding of this. Okay? Right? Okay. Okay. But to derive the necessary running time bounds, we are going to assume that Oracle has some beautiful properties. Okay. But these are the kind of Oracle. So we would like to have an Oracle for such kind of problem. Okay. And we will see how to construct such an Oracle for large classes of problems later. Okay. Now we know this, so if I want to apply this, I need to this in -1 to 1 and blah, blah, blah. Okay. Now, what do you mean by running time bound? Look, I cannot just go on. Otherwise, like if I want to show that this algorithm will terminate into certain number of steps, right, which is like certain number of days, right, then I need to do something about it, right? I need to have this Oracle also efficiently solving me, and it is going some way forward each time. Okay. Okay. So generally what people use is what is called row bounded Oracle, but what I'm going to use is something called L row bounded Oracle, which I found in the paper of this paper, which seems slightly general. Yeah. Okay. This is called L row bounded Oracle. So this is a technical definition. This is called bounded Oracle for parameterized, for parameters 0 L P is an algorithm given a probability vector over its constraints solves the feasibility problem star, okay, solves the feasibility problem star, okay. Furthermore, there is a fixed subset I of 1 to m, like where m is number of constraints, okay. So that whenever Oracle manages to find a point x in P, okay, satisfying star the following holds. For all I in I, okay, AIX minus BI, look at the row I and this vector. This constraint is BI is between this, like look at this value, it's between minus L and rho. And for all I not in I, AIX minus, so this is the lower bound times L. Okay, so think of this way, here 0 less than equal to L less than equal to rho. So what is this? This is minus rho, this is plus rho, right? And this is minus L and this is plus L, right? Now what does it say is that for all I in I, this value is here, right? And for all this is here, right? But many people just define row bounded oracle and then all say for all I, this like mod value is between minus rho and rho, right? But here you are also given some lower bound and given an upper bound. So it allows for many problems to get a refined bound. But if you do not understand, substitute, forget L, you just say row bounded oracle, right? So when you substitute L equal to rho, you get, okay? So most paper or books will deal with you L equal to rho, which is like, it's called row bounded oracle. Then we can say for all I in M, what happens? Mod I AI minus BI is greater than equal to rho, right? Greater than equal to rho or less than equal to rho? Huh? Less than equal to rho, right? No? Should be greater than equal to rho or less than equal to rho? Huh? Less than equal to rho. Correct. Right? This is what it means. So this is what our oracle will be. Okay? And this rho is also called width of the problem. Okay? What is rho called? Width of the problem. Called width of the problem. Okay? Given these oracles, okay, now I want to prove the following theorem. Okay? So this is a theorem which I would like to prove. No, I have always followed this. Let epsilon greater than 0 be a given parameter. Be a given parameter. Okay? Suppose there exists L row bounded oracle, okay, for the feasibility problem star. Okay. Assume that L is greater than equal to rho by 2. I mean, it's a technical condition. No, epsilon by 2. Then there is an algorithm algorithm that finds x in P, finds an x such that for all I, what is this? Ai minus x is greater than or equal to bi minus epsilon. Okay? If this happens, look, it satisfies, right? Now, all I know is this happens, ai minus x is greater than or equal to bi minus epsilon. Or correctly concludes that the system is infeasible. Okay? The algorithm makes how many calls? The algorithm makes, so look, we are only decision version of the problem. So if we found a solution which is more or less feasible, I know how to make it completely feasible by dividing by 1 minus epsilon. By dividing by, by dividing by 1 minus epsilon. Right? This is what we did. Then the algorithm makes order, see this is where all the things will come, L rho log m over epsilon square. Then the algorithm makes this much, calls to oracle. Okay? With an additional preprocessing time, preprocessing time of little, preprocessing time of order m. Notice, if I would have been applying an online algorithm, this and that, I wouldn't care about time. Okay. Okay. So now what happens? So as I told you before, now we have to map this situation to our general situation, which we have been dealing with. Okay. Okay. So what did we say before? Expert corresponds to constraints. So this is our proof. To constraints. And what is my event, or what is my outcome if I chose a particular this thing, is events correspond to vector x b. Okay. And loss, penalty, whatever you want to say, cost, loss of the expert corresponding to constraint I for an event x is how much? 1 by rho this is my cost. What is AIX minus BI? Like something. And why did I divide by rho? So that they become element of -1, 1. right? So that, look, our proofs only work, this proof worked when the cost vector lies between minus 1 and, so I have just re-scaled them by rho, so that this, because I know that this value is never more than rho, right? Because what I'm giving, what are we given us? We have been given an oracle that returns all the time a solution which satisfies this set of constraints, right? So the maximum value this oracle can take is rho, right? So maybe this is minus rho for all this I know, but if I divide it by rho, I get into minus 1, right? So this is the cost which I'm giving to him, right? So basically, now tell me, when will someone get, for now let's say think positive, right? When will you, look, all I want, suppose AXI minus BI is greater than or equal to 0. It means AIX satisfies BI, right? AXI satisfies BI. Then at that point, so this, if this is greater or equal to 0, right? Then what is it, like, then I shouldn't care about this. Like, this guy is like, I shouldn't be caring about, this guy should be costing us way more, right? So that I can forget him. What is our idea? Our idea is to forget those curves. Suppose this is satisfied, it means this is greater than or equal to 0, right? And if it is not satisfied, what happens? If it is not satisfied, right? So look, everybody, I actually at the end I want all this to be greater than or equal to 0, right? But what could you happen, right? I want greater than or equal to 0. So this side is great for me, but here I have chosen minus rho, so you could be somewhere here, right? So what is this value getting then? If you look at those values, so for AIX minus BI, right? If it is negative value, if it is negative, what is its cost? Right? It's something less. So its cost is much less. But when you are positive, right, your cost is much larger, because cost ranges between minus 1 to 1. So if you are satisfied, I'm charging you much more, right? I'm charging you positive quantity. But if you are not satisfied, I'm charging you negative quantity, right? So like, if you look at this constraint, what does it tell us? Suppose it is greater than or equal to 0. If it is greater than or equal to 0, then rho is a positive quantity. So if you are multiplying something positive divided by, like, if you are dividing something positive by positive, you are only going to get a positive quantity. And if something is under satisfied, right, it is not yet satisfied, its value is going to get negative. So with respect to all those guys which are already satisfied, they all are going to get positive cost, and all those constraints which are not satisfied is going to get a negative cost. It means what? Like, the people who are going to cost me a lot more, let's forget those experts, right? Or give them less amount of weight, right? Let's only concentrate on those experts or those constraints which are not yet satisfied. And this is what I can achieve by giving such a cost vector. Is this clear? Right? So this is where this negativity helps us. So everybody who is satisfied is going to give me a positive cost, right? Everybody which is unsatisfied is going to get me a negative cost. Now, this will differ how close to satisfied or unsatisfied you are, right? If more you are unsatisfied, much less costing you are costing to me. Now that we have understood satisfied versus unsatisfied, look at even unsatisfied. If I am really far away, then I am costing you even less. But if I am very close to being satisfied, I cost you still much more compared to the other guy, right? So this is an intuition of this cost vector. Okay. Okay. So hope. Okay. So you understand the intuition behind giving this cost, and now it's everything starts to make sense, right? Experts are my constraint, this is my cost vector. Like this is exactly what we said. If an expert was like incurring lot of cost, right, then we were reducing him, right? We were giving more weightage to those experts which were correct or which were costing us less or which were rather correct. So like I have just changed the scenario now, right? Which in this setting will mean now please concentrate on those constraints which are undersatisfied. Okay. So we should rewrite this algorithm a little bit, but that will not be multivariate weight algorithm, but that will be multivariate algorithm for covering LPs. For feasibility of covering LPs. Okay, we'll try to rewrite this slightly. Okay, okay. So this is the cost vector which we are going to give. Okay, so now this algorithm, I think I might make a mistake. So please be aware. Okay. Okay, so I will just choose, like I am not choosing an expert or anything, right? I'll just choose, I'll just slightly change this just to reflect whatever we just talked. Okay, so what I will say, right? Let x of t, okay, everything like for t equal to what it was here, 1, 2 to the t, okay. Let xt be the solution returned by the oracle, okay. With respect to this weight values. Look, our oracle took this probability distribution and tried to, right? So with respect to this, nothing changed here. Okay. Now observe the cost vector MT, but now we have to define what cost vector means, right? Okay. So now our cost vector is MIT. If I told you MIT, what is this? Then you know what this is. This is AI, ith column, xt minus bi divided by rho. This is exactly what I explained to you here, right? But now x is not, but it's a teeth round x vector, right? This. Yeah, that's it. Right? And notice here that, let's just write, that's it. My algorithm is done. Like this is all the changes which I wanted to do, right? It's not very clear that it will give me a solution to LP, feasibility LP, right? So just a small remark here, which we just observed. If MIT is greater than or equal to 0, means I is satisfied, otherwise not. What? What eta and rho? Cost should be also eta, no? No. This cost is this oracle cost. This row is at oracle row. This is an oracle's row. This is not the eta. So these are different objects, right? But look, I have to decide a cost vector, so I can define a cost vector. Okay? So this is my algorithm for covering LPs. Okay? We have already done all the analysis and everything. All we have to just do is, okay? So I have written down all the algorithm. I told you why this means whatever we want it to mean exactly in the right sense. Okay? And now let's see. Right? So look, this is a step which gives us a control over which constraints to look for in the next step, right? This is exactly why this term or steps come in. Okay. So Oracle, I think we should also be, let xt be the solution returned. If returns infeasible, say no, because it could return infeasible, right? So I should return no at that point of time. Okay, so let's assume that we never stop. Like if at any point of time, because we know if Oracle said no, then it's infeasible system, that's perfectly fine, right? Because for any probability vector, I told you that if something is satisfied, then this linear combination of like convex combination of these PIs with this constraint is also always satisfied, right? So if something is satisfied individually, they are definitely satisfied on average, but if something is not satisfied on average, it cannot be satisfied individually too. Okay. So let us assume that Oracle never returns infeasible. Okay, it never returns infeasible. So for all round t, it finds a solution x of t such that p transpose A x of t is greater than or equal to p transpose B. Right, this is what it means. Oracle, it means for all round 2 we are able to find x of t such that this happens. And what is the weight? So, look, if you recall correctly, this empty PT is never 0, never negative. We saw last time also this is never negative. Why? Let's look at this. This is positive quantity, right? This is positive quantity. Look, PT is never negative. PT is never negative because this is a probability distribution, so greater than or equal to 0. But what is empty? This quantity could be negative, but is empty dot PT could be 0? Anyway, let's write it down. So what is empty dot PT? Is equal to 1 over rho empty times PT is 1 over rho A xt minus B vector dot P transpose. Agreed? T empty is nothing but this vector, right? And you are taking a dot with this, which is nothing but taking dot with PT, right? And 1 by rho is sitting here. Like, see, think of this way, right? What is this? If you look at A xt minus V, what is A xt? It is going to give you some numbers here, right? And you subtract minus B from here, and you are taking dot product with P of t. This is exactly what is happening here. Like AI x transpose is some number, 1 by rho common. This dot this is nothing but this. What? Yeah. Okay. So this is this, right? Which is equal to 1 over rho. But what is this? A x transpose P transpose x. Haven't I wrote something wrong? Correct, right? Is B, right? So this object is greater than or equal to P transpose. This object is greater than or equal to P transpose B, right? So which is I think it should be PT transpose time B, because PT is a column vector, right? No? PT of the transpose, right? Whatever. P transpose B, right? Because P is a column vector. So rho times P. So this is equal to, let's see if I'm making correct. So I want to multiply this both sides. So since this is a number, it doesn't matter if I multiply them here also, shouldn't it be PT transpose, right? Otherwise it doesn't make sense, right? So I take this, then I can write down this is same as P transpose P of t transpose A x of t minus B. I want to get him before him, so I can get him P transpose P of t transpose B, right? And what do we know about this is greater than equal to this minus this is greater than equal to 0, right? So this is greater than equal to 0, right? Because oracle returns x with this quantity, so this is greater than equal to 0. You are dividing by some positive quantity, so this is greater than equal to 0. Okay, now it's time to apply our theorem. What did our theorem told us? What did our theorem told us? That the best expert is less than something, or the amount of errors or whatever you want to say. So total amount of cost which the algorithm will incur is upper bounded by the maximum blah expert will occur, right? So I can write down, right? So now what is the cost of an expert? AI rho xi. Which should I rub? Should I rub this or should I rub this? I think I need this. Okay. Let me. Okay. So all I want to say now, I wanted to apply the theorem which I proved. 0. So what is this? This is the cost incurred by the algorithm. This is the cost incurred by the algorithm. Do you realize? This is the cost incurred by the algorithm. Sum over t. Right? That is the cost incurred by the algorithm is sum over t. But if each term is greater than or equal to 0, the sum is also going to be greater than or equal to 0, right? Okay. So what I am saying to you is summation over t going from 1 to t, m of t, p of t. This is what we know is less than or equal to, because we proved this theorem, summation equal to t equal to 1 to t for any I, this is true, right? AI xt, this is the cost, minus b, bi, right? Minus bi, this is true with respect to every I. So, but let me fix this, plus eta time summation t equal to 1 to t 1 by rho mod, if you recall correctly, right, minus bi, right, this is eta times plus ln m by rho. Do you agree to this? This is exactly what we proved this. Now, if each of them is greater than or equal to 0, so this is also greater than or equal to 0, because each term is greater than or equal to 0. MTPT is greater than or equal to 0. So their sum is also greater than or equal to 0. So 0 is less than or equal to this quantity. Now what is this? this is equal to 1 plus eta 1 plus eta. Look, if I make mistake, please let me know, okay? Because I am not very great with all this computation. Summation, I want to take this and this together. Okay, let's see. 1 plus eta 1 by rho ai xt minus bi. So look, there are some quantity here where this is greater than equal to 0, and there are some quantity which is less than equal to, strictly less than 0. So greater than equal to 0, I forget mod and I got them here, right? But only for some quantity, right? So like this plus rho times that. So, or think of this way, so here I added that guy here, okay, plus ln n by rho. Let us see why this is equality. This is equality, it seems, okay. So if I take this, this is exactly this term, right. So this term has eta times this term, and here I have forgot those terms where it is positive quantity, right, and I have added them here, but not everything I am adding with rho, right. There are some quantity here which happens with negative. And the positive quantity there. Is that not what is happening? But why we are getting 2 times? Huh? Yes. Correct. Right? Because it was a mod, right? It was mod of the negative, right? So I added them here, so I have to also add the rest there. Subtract there, right? Because it was a mod quantity, perfectly. Okay, so I added them here, right? So this is why it is this times rho times this quantity. Yeah, this is fine. Which is less than equal to 1 plus eta summation t equal to 1 to t. This is also t equal to 1 to t 1 by rho, let us not change anything here, x transpose bi 2 eta look, but they also had a lower bound of what? Look at, these are the less than 0 quantity, right? They are negative. So their negative means where? Here. Look, this is minus rho, this is plus rho, minus L plus L, right? What does it tells you? This quantity is between here, or this quantity is between here. Look, either you lie here or you lie here, and here is a 0. These quantities are less than 0, so you are here, right? So what is the upper bound on the absolute value of each quantity inside? Rho or L? This quantity here is upper bounded by L. We are doing less than equal to, right? Look, these are negative quantities, okay? So negative quantity shouldn't there be should be L here? Wait. Yeah, you should think, look, if for a positive quantity, suppose this is positive quantity, let's think for a minute. Okay, okay, I think I understand now. Look at suppose if you have a positive quantity, where are you lying? You are just lying between L and rho, because there is nothing in between here. You cannot lie here. Look, suppose you are a positive quantity. Is something missing here? If it is strictly less than 0, somehow they claim that this is bounded by L. Let's see why. There should be some silly reason for this. What is happening? Okay, so I'm being stupid. Okay, so this is a case when I is in I. Okay, I is in I. So if I is in I, then clearly upper bounded will. Look, what I'm trying to show to you. Or conclude that this system is infeasible, right? So now for the analysis, I'm trying to do these things in a different way. So up until now here is fine. Now I'm assuming that either I belongs to I or I does not belong to I. If I belongs to I, then this is definitely upper bounded by L because this is what you can get because it is less than 0. So this is, otherwise this is like, so this is 2 n L by rho, okay? This is fine, right? Times, I can write it down T because maybe it's all, like all the rounds, this is what happens, plus like T plus ln m by rho, okay? But this is true, like this is true with respect to every constraint. So this is, we can just forget it. So now let's divide by T, because this is greater than equal to 0, I can divide by T. So what will we get if we divide by T? We will get, if I divide by T and multiply by rho and multiply by there's something, am I, this is exactly what I'm saying, thinking that why is this stupidity happening? But this is rho, okay? This is fine. This is also not right. Please tell, right, all this. I mean, as I have told you several times, I do have issues with things of this nature. So divide by T and multiply by rho. So what will we get? 0 is less than equal to So rho will go from here, rho will go from here, 1 plus eta by t summation t equal to 1 to t 1 by rho ai x of t bi rho, and we are multiplying by rho dividing by tau. So 1 by rho, rho will go from here, rho will go from here, t will go from here. So you will get 2 eta L ln m by rho. What? What? I didn't get it. So I am dividing by t and multiplying by rho. Is this? Okay. Here you are saying that there should be a t here. No. This.
So it's ln m into rho divided by eta t.
Rho eta t. Fine. Okay. What?
First term 1 by rho has to be.
Why? This will go away. No? This is what I meant? Okay. Thanks. Let x bar be equal to 1 over t summation t equal to 1 to t xt. Suppose this is what it is. Okay? Then what will we get? 0 is less than equal to 1 plus eta, right? So this is what I have taken x bar equal to. So this will become ai dot x bar, ai dot x bar, because it is summation, right? And is this correct? This is fine, right? Because I am only saying less than equal to, right? All the other, I mean, if I do this, t into bi, right? Right. So I should have, okay. Yeah, so there is a t here, right? Right, there is a t here. So if I took x equal to 1 by t here, right? So this is going to be bi times t, because it is going to appear t times, right? So this is going to be bi times t divided by t, because we had 1 over t here, right? Plus 2 eta L ln m rho eta t. So T gets cancelled. My God. If we choose eta equal to what? X bar, I assume that this is equal to this. Okay. Now choose eta equal to 1 over epsilon over 4L. Okay. What does this imply? Eta is less than equal to half, since L is greater than equal to epsilon by 2. Somewhere I have chosen, right? L is at least epsilon by 2. So eta is at most half. Anyway, I always assume eta is less than equal to half. That doesn't matter, but that's fine. So what do we get? and T equal to chose eta equal to epsilon 4L and T equal to 8L rho ln m by epsilon square. Then what do you get? You will get something here. If I set all these parameters, I set eta equal to epsilon by 4L, right, and T equal to this, okay. Then notice that 0 is less than equal to times AI x quantities. What are these quantities? They will be like epsilon. All these quantities now have bounded as epsilon, right? Because, right? So T is like some 8 L rho m, right? So ln m will go cancel, right? Rho will cancel. Yeah, something should happen, just wait. This should be less than equal to epsilon, that's all that I am saying. Okay. Why? Because what is this like? 2 eta L, right? It should be 2 eta L, right? What is 2 eta L? Is less than equal to epsilon by 2. Agreed? Huh? Yeah, fine. Fine. Okay, so this is one. Second is, what is it? Ln m times rho eta times T. Did I fix rho? Huh? What was T? Huh? Oh, eta is? See, you people can do. Equal to what? Okay, so this will epsilon by 4L. Is that what it is? Okay. And T equal to, put those numbers, 8L rho ln m times epsilon square. Huh? My God. So what do we get? 1 plus eta, wait, right? Very good. So this is what we get. So now from here, what will we get? Can I say this? AI x bar minus bi is, what is eta? Epsilon by 4L. Is this correct? I did this here, it's minus epsilon, right? This is fine, right? Because look, divide by 1 plus eta, right? So this is greater than or equal to minus epsilon, because this is some positive quantity. So that implies AI x bar is greater than or equal to bi minus epsilon. If I is inside this, if I is not inside this, do the same analysis, you will get some other epsilon and delta. So what did you learn from here? This is it, right? So imagine that if you would have guessed the right value, what will be your, say for example, minimization? If you would have guessed the right value, your opt value is not going to be more than some 1 minus, like if it is minimization problem, it will be epsilon times this. But notice all the time, so what is this oracle tells us? Oracle tells us that, okay, I'll give you p value, please find where it was. P T transpose Ax should be greater than equal to P T transpose B. When will this happen? Think of this way. It just basically it boils down to maximizing this function. Look, if I want this to be greater than equal to this, if I find the maximum value of this, right? If that is not greater than equal to this, then I can definitely say it's no instance, right? If you wanted me to give me this, so if I just maximize this value for x, like a is given to me, p is given to me, only thing which is given. So if I maximize the value of x for which, like over my domain, if I maximize this, and if that itself is less than this, then there is no way, right? So generally what we will try to do, that in our problem, we'll try to maximize this constraint, which will be very easy to do. Like for example, for set cover, it will be just selecting a set which covers, like which has most number of uncovered elements, like, or sum the weights currently probability distribution whose weight is large. We'll do that next time, okay? So this is how you use it for the convex programming or the like LP and all, feasible problem, okay? So this is what weight of myth. Now I still have not given you a concrete example, right? But if you, so here's an exercise. Try to apply to this set cover example and see what happens. Right? So I did it in very abstract setting. I didn't do it in very, like, so how do you, like, so what I did not teach you, how do you take care of this oracle? What L and rho to choose? That is very problem dependent. But in general, the basic methodology which 99.99% time works, you get one constraint, you choose x which maximizes this. Okay? You output that x as your, as the oracle answer, and you keep going and you will have the guarantee. Now, what is a domain? Like what will be this L rho business we are talking about, rho, right? You can show that if you try to maximize this, it will be, rho will be like the min value or the max value. The domain value will be like opt. So it will be like opt bounded oracle. So the role of rho will be played by opt. So it will be opt bounded oracle. So we can get an opt bounded oracle by, in most cases, by just maximizing this function. Because if I maximize this, at it is infeasible, forget it, right? Okay.